today we're going to be studying the Fundamental Theorem of Algebra. This is something that is really important for upper-level math. Just as important as the Pythagorean theorem was to geometry, the Fundamental Theorem of Algebra is to Algebra 2, Pre-Calc, as well as Calculus. We are going to use this theorem to help us find all zeros of a polynomial function. Then we want to also be able to work backward. If we have the zeros, we want to be able to use it to come up with what the equation of that function was. So the Fundamental Theorem of Algebra, in its beginning, doesn't sound too exciting. It says if a polynomial has degree greater than 0, so that means has a variable, because degree 0 means it's a constant, means there is no x. So if you have a polynomial that has a variable, so at least an x, then its equation, if you set it equal to 0, has at least, meaning it could be more, one root in the set of complex numbers. So basically that means if you have at least an x, you have at least one solution. It might be imaginary, it might be real, but there's going to be at least one solution. Now, when we go further with the Fundamental Theorem of Algebra, we find out there's more to it than that. We find out that a polynomial of degree n should have n solutions. Remember that the words, and I'll use a different color here, the word root, solution, zeros, x-intercepts, those are all synonyms for each other. So when we say a polynomial that has degree n will have n solutions, that means it'll have n x-intercepts, n roots, so on and so forth. So if it's degree 5, it should have 5 solutions. Now, only the real zeros will appear as x-intercepts on the graph, because when we are graphing, we cannot see the imaginary solutions. So only the real ones will be seen on the graph. Imaginary solutions are always going to come in pairs. So we learned about complex conjugates back in Unit 2 when we first studied imaginary numbers. And if you had 5 plus I, we knew the complex conjugate was 5 minus I. So those are examples of complex conjugates, but they always come in pairs. So we are going to use this to help us know when we have found all of the solutions of a given polynomial. So example 1, we need to find all the zeros of our given polynomial. So I have x cubed minus 4x squared plus 3x. Since this does not have a constant term, that means that I can't use my rational zero theorem here. So that means I'm going to go straight to graphing it. So I graph it first. And again, this is just a rough sketch that you're writing down, but I need to see that you have done this. So yes, I need to see your sketch. So you do a rough sketch, and it looks something, and I always draw in what I think my x-intercepts are first and then kind of connect the shape. Okay, so it kind of looks a little bit like this. And it looks like, and I always write this down, I encourage you to do this as well because you need to record it somewhere. So I just write looks like and then what the zeros are. It looks like 0, 1, and 3 might possibly be zeros of that given function. So I need to pick one and do synthetic division. So I'm just going to start on the left side. So I'm going to start with 0 here. So if I pick 0, 0 goes in my box. My coefficients, x cubed, it's a 1. My x squared coefficient is -4. My plane x is a 3. And then my constant was a 0. So draw my vertical line. Bring down my first term. Box times bottom is 0. Add the column, which is -4. Box times bottom, still 0. Add the column. Box times bottom, 0. Add the column. I did get remainder 0, which means that 0 is indeed one of my roots. It is indeed one of my solutions. So now I look. I started with a cubic, which means that this represents a quadratic. So this represents x squared minus 4x plus 3. So I need to solve that because right now I only have one zero that I actually have work for. So I'm going to set this equal to 0 and I'm going to solve the quadratic. This one happens to be factorable because the factors of 3 that add to negative 4 are negative 3 and negative 1. So since that is factorable, if x minus 3 equals 0, that means x equals 3. If x minus 1 equals 0, that means x equals 1. You have to have work for every zero. I'm going to write that in big letters up here. You must have algebraic work for each zero, not just graph work. Algebraic work for each zero. So you can see I've got 3 solutions here, which should make sense because the degree is 3. So 3 solutions. My work for x equals 0 is the synthetic division. That's algebraic work. My algebraic work is down here for x equals 1 and x equals 3. So those are my 3 zeros. I know I found them all because 3 is the degree. I can't have more than the degree. All right, let's try this again. So I look here on my equation, x to the 4th plus 5x squared minus 6. Here I have a constant term, so I can list my possibles. The factors of 6 are 1, 2, 3, and 6. Factors of the leading coefficient are 1, which just basically means plus and minus 1, 2, 3, and 6 are my possibles. So I look at my graph. And my graph is pretty skinny. It looks something like this. And so the zeros, it looks like it crosses at -1 and +1. So I'm going to pick one of those to confirm. So I'm going to start with -1. I usually start on the left, so -1. I need to write down my coefficients. The degree here is 4, so I should come up with 4 total answers for my zeros. So coefficient of x to the 4th is 1. After x to the 4th comes x cubed. Don't forget those placeholders. There was no x cubed term, so I need a 0 in there. X squared coefficient is 5. The plain x coefficient needs a placeholder of 0. The constant is -6. So now bring down my 1. Box times bottom is -1. Add. Box times bottom again. This time is +1. Add to get 6. Box times bottom is -6. Add. Multiply. And I do get remainder 0. So -1 is indeed one of my zeros. Now, this was a quartic. We did these in section 6.6. When the original polynomial is quartic, you can't just do a single synthetic division because more than likely your cubic is not going to be factorable. Now sometimes they are, and if it is, feel free to factor it by grouping with its 4 terms, but many of them will not be, which means you need double synthetic here. So it's a good thing that when we looked at the graph, we saw more than one. I saw -1 and I saw +1. So to do double synthetic, I now set up the +1 with the answer from the first synthetic division. So here's my new remainder column. Bring down my 1. Box times bottom is 1. Add the column to get 0. Box times bottom is 0. Gives me 6. 1 times 6 is 6. And that gives me remainder 0. So I have now confirmed x equals -1 and x equals 1. And now I have it down to a quadratic. So this represents x squared plus 0x plus 6. So I set it equal to 0, and I need to solve that. This one is an easy quadratic to solve because I can solve it with square roots. So subtract the 6. If x squared equals negative 6, square root both sides. And x equals, don't forget your plus or minus. Square root of 6 doesn't simplify, but because there's a negative, I need an I in my answer. So plus and minus I radical 6. And then don't forget to list your other two, which were negative 1 and positive 1. I'll just list those with a plus and minus also to save room. So again, you double check when you finish each problem. Look at the degree. This was degree 4. So I have 1, 2 solutions with the i's, the plus and the minus, and 1, 2 solutions with the plus and minus 1 for a total of 4. So I have them all. All right, so hopefully that's not too tough, just kind of extending what we did in 6.6 and now knowing whether we have found all of the solutions or not. Example 2 is new, and now we're going to be working backward. It's for our second learning goal. We want to be able to write a polynomial function when we're given the zeros. Now here's a couple things that's important to remember. When you're writing this, we're going to need to put x's in. These are just numbers. So if k, a number, is a 0, then that means x minus k is a factor. That's what we did when we did the long and synthetic division to begin with, when we had, x cubed plus 2x minus 1 divided by, x plus 5. And we said, if you're dividing by x plus 5, that means negative 5 is your factor. So it works the same way here. If 3 is a 0, that means x minus 3 has to be a factor. So I'm going to write that. X minus 3 is my first factor. My second factor is x minus 0. And my third factor is x minus negative 2. Remember that minus negatives become pluses. So I used that important reminder to write this together. Now, x minus 0 is just x. So we're going to rewrite this, x times x minus 3 times x plus 2, because that's more simple. And now we need to multiply. So this is just what we reviewed in 6.3, which you guys did very well with. So here you can either distribute the x first and then FOIL, or FOIL first and then distribute the x. It doesn't matter. I'm going to go ahead and just go from left to right. So I'm going to distribute my x first, which gives me x squared minus 3x. And then I am going to FOIL that with my x plus 2. So firsts, x squared times x is x cubed. Outsides, x squared times 2 is 2x squared. Insides, negative 3x times x is negative 3x squared. Lasts, negative 3x times positive 2 is negative 6x. So now, like terms here in the middle, x cubed minus x squared minus 6x is a polynomial of least degree. Meaning, this is the lowest degree we could write, is degree of 3, that has these zeros, real coefficients, and a leading coefficient of 1. So x cubed minus x squared minus 6x is your answer. Now, you notice I have a second hint here, and we put this up at the beginning, that imaginary solutions always come in pairs. That's what complex means, imaginary. They're always paired. That's important because they don't always list both of them for you. So I start off the same as I did over there. If 5 is a 0, that means x minus 5 is a factor. If 2i is a 0, that means x minus 2i is a factor. But because complex zeros are always paired, that means that if 2i is a 0, that negative 2i has to be a 0 also. So even though they don't say it, it has to be true because they always come in complex conjugate pairs. So negative 2i must also be a 0, which means that x minus negative 2i would be x plus 2i. is my other factor that I need to write. Now, with these, always FOIL imaginaries with each other. And do that first. So, when I do my FOIL on those imaginaries, first, x times x is x squared. Outsides, x times 2I is 2ix. Insides, negative 2I times x is negative 2ix. And my lasts, negative 2I times positive 2I, blast from the past, remember how to do this, negative 4I squared. And hopefully a little red light is going off because you remember that this is something special. Now to simplify that, these cancel each other out. This is why we always FOIL the imaginaries with each other, because those inside and outsides are going to drop out, and because my I squared, I know that that's negative 1. So negative 4 times negative 1 is positive 4, so that's just x squared plus 4. So always FOIL imaginaries with each other because it is so much less messy. If you try to FOIL the x minus 5 with the first imaginary, it's going to be a giant mess. You're going to have to create a box, and there's just going to be all kinds of nonsense that you don't need to have. So FOIL the imaginaries with each other first, and then bring down your others. Or if there are two others, you can FOIL them with each other. And so now I can FOIL that. So x times x squared is x cubed. X times 4 is 4x. Insides, negative 5 times x squared is negative 5x squared. And lasts, negative 5 times positive 4 is negative 20. Now, write your answer in standard form. There aren't any like terms, but I do need that in standard form. X cubed minus 5x squared plus 4x minus 20 is my standard form polynomial with these given zeros. All right. That is it.